start out with any questions on, we'll just start with chapter 4. We'll get to chapter 5 in a moment, but any questions on chapter 4? Anyone about to come up with a question on chapter 4?
Yeah, I am. Could you do a different iteration of 52?
Excuse me?
Could you do like a different version of it, number 52? So I can change the numbers or something?
Alex, who has a mass of 100 kilograms, that one?
Yeah.
All right, so we'll make the mass 90 kilograms. Let's give him some good speed here. 30 meters per second. He's going over 60 miles an hour. And then he hits the brick wall. So initial speed. We're doing forces, so we'll just say initial velocity. And then he stops in 0.1 seconds. So his deceleration. So he basically he's stopping in 0.1 seconds. So he goes from 30 to 0 meters per second. So that is his final velocity. And the question is, what's the acceleration? Well, change in velocity over change in time. So what's this change in velocity? Oh, you skipped a step. What's the change in velocity?
30 per second.
Oh, that meters per second, is that what you're going for?
Right?
So you said,
That's 30 meters per second. You looking for that, or?
almost that.
Okay.
Change in velocity is not 30.
Negative?
Yes. Change is negative 30. So negative 30 meters per second over the time it takes, so 0.1 seconds. So then you get negative 300. Sorry. Negative 300 meters per second squared. So that's his acceleration. Now the question asks for deceleration. Oh, sorry.
I don't have that.
Okay. The question is asking for what is his deceleration. In this particular case, he is slowing down. It is a negative acceleration because I made his initial velocity positive. So by making this positive 30, I indicated that he is traveling in the positive direction when he hits the wall. And therefore, the acceleration will be the opposite sign. Deceleration is just automatically builds into it. He's slowing down. And so the answer would be 300 meters per second squared, given the wording that Hewitt uses for part A. I suspect that would kill him. It's more than 30 Gs. Part B. Show that force of impact is 4,500 newtons. F equals ma. His mass is given. The acceleration we just found. I am going to keep the negative sign in there. Ultimately, he's ignoring the signs. so that's negative 27,000 newtons. Or kilogram meters per second squared, if you want to go that route. And, oh, that's it, A and B. Is that what you were looking for?
Yeah,
Okay.
I just wanted to do another one.
Okay. Yes.
Okay, so in the two, why wasn't his negative? Because it's. Yeah,
The negative sign is a directional thing, and deceleration,
okay.
it's, if I started going up, I'm just gonna go for an actual answer here instead of partial words. From a physics point of view, positive velocity, negative acceleration means that he's slowing down. If the signs are opposite, he's slowing down, because the force is opposite the direction of movement. Deceleration is not really a physics term. Deceleration, which is what he does in his problem, is built in that he's slowing down. Unlike the word acceleration, which could be several different things. But deceleration already it's not a physics term, it's a everyday language term, meaning you're slowing down at what rate. And so, since the word slowing down is already built into that deceleration, he's slowing down at a rate of 300 meters per second every second. That's why the minus sign goes away.
This is kind of confusing, because I was gonna ask the same thing that he asked. Because like in the problem, it's not negative, but you did it as negative. I know you just explained it, but it doesn't make sense to me.
The plus or minus is purely a directional thing.
Okay.
So, I could have, just as easily on that first part, all right, I got brick wall here, or, it is a brick wall? Brick wall. Skateboard. When I did first work the problem, I just said that's the positive direction. So velocity's positive, acceleration's negative, because when he hits the wall, he's gonna be forced, the normal force is in that direction on him. If I said that was the negative direction, then he goes from negative 30 meters per second to 0 meters per second. So acceleration will be the change in velocity, which is positive 30 now. If you're going from negative 30 to 0, you have to add 30 to get there. Over 0.1 seconds. So I get 300 meters per second squared. It's just as legitimate an answer. The positive just means it's in the, ultimately the force is in the positive direction that way. He was trying to, what Hewitt was trying to do was avoid the whole mess of positive or negative. Because they're both correct answers, all depending upon what I decide is the positive direction.
Okay. I just didn't want to like have the right answer and then just get it wrong because it wasn't positive or negative.
Yeah, so that's why when you use the term deceleration, that's sort of the scalar term, you're gonna get a positive answer in that. He could have also just said, showed that the magnitude of the acceleration is, well, this problem, 45 meters per second squared. Magnitude also ignores direction, so the plus and minus go away. I hope that's sufficient, or
Yeah,
if not,
that's
you.
good. No, that's fine, thank you.
Other questions from chapter 4?
Yeah, I have another question. I can't find a problem about it, but could you do an example where you have like a box that has a certain mass being pulled with a force both like right and up?
Oh, right and up? Okay. You said pulled, so. Uh, 4 kilograms, 5 newtons, 8. Is that this type problem?
Yes.
Alright. And you wanna find acceleration? What,
What, I don't know, whatever you would ask us to find on a problem like this. Like, I
Alright,
guess
so-
the resultant
so-
vector or something.
A. Total force. B. Magnitude of total force. C. Acceleration. D. Magnitude of acceleration. The absolute value signs are just saying I'm looking for magnitude, just the amount, I don't care, I don't want the direction in this answer for B and D. Alright, so, the total force, I have two forces acting on it, they're in two different directions. The simplest way of adding them is to create I hat and J hat. Unless you like feeling like writing out to the right and up. So the total force is, well, I got 5 newtons in the I hat direction. And I have 8 newtons in the J hat direction. That's the total force right there. Again, this is rectangular form as opposed to polar form for those who've come across that in math. The magnitude, now I need to somehow get rid of direction, so I don't just drop I hat and J hat and add them together to get 13 because they are in different directions. I still am adding the vectors. I have a vector going to the right of 5 newtons plus a vector going up of 8 newtons. So my resultant is that vector right there. That is a right angle. And so, little Pythagorean theorem. So that would be the square root of 5 squared plus 8 squared.
It's 9.4.
9.4. So the vector in polar form is 9.4 newtons in whatever direction that is. And you can use trig to figure it out. But the question is only asking what's the magnitude. In other words, I'm asking for that number right
Bless
there.
you.
So this would be 9.4 newtons. And then acceleration, F equals ma. Well, I know the force, I know the mass. If I'm solving for acceleration, well, I divide by the mass. Five newtons I hat plus 8 newtons J hat divided by 4 kilograms. So I got this expression on top with a plus sign in the middle divided by the 4, which means I have to divide both things by 4. Paralleling back to math class, I'm distributing. So 5/4, 1.25 I hat, and then 8/4 plus 2 J hat. And of course, units. Meters per second squared or newtons per kilogram for those of that inclination. And then the magnitude of acceleration, there are a couple ways of doing it. If F equals ma, which we are definitely assuming is true, then the magnitude must be equal. Well, mass is a scalar, so I can just factor that out. So this is the magnitude of the force is equal to mass times the magnitude of the acceleration. So I could just take the 9.4, which has already been calculated, and do 9.4 newtons divided by 4 kilograms. Something less than 2.5. 2.25?
Yeah, 2.25.
Units?
Meters per second squared.
It's acceleration, yes, meters per second squared. Or, we have it in rectangular form, we could just have done Pythagorean theorem and we should have gotten the same answer. If we do not get the same answer, something has gone awry. That one. Did that satisfy your need for the moment?
I have one more question
Okay.
on the, let's see. When you were finding the, let's see, the vector of acceleration, how did you know that the units were meters per second squared?
When dealing with standard units, SI, standard international standard. Speed, velocity, meters per second, force is newtons, acceleration is meters per second squared, and so forth. It just, because it's acceleration, I know it's meters per second squared. More formally, a newton, by definition, is a kilogram meter per second squared, by definition. So newton divided by a kilogram is a meter per second squared. But primarily it's that, I started out with standard units, I'm gonna end up with standard units in the end. Now, I have noticed some students struggle with knowing which units are standard, in which case, newtons over kilograms would have worked. Other questions from chapter 4?
Number 57.
57. Oh. Good. I don't have it circled here. Was that one of the required, was that one of the ones on the list?
It wasn't.
I'll be glad to go over 57, but
It's under the chapter 4 homework in the first one. And then, in the thinking rank thing. I think it was on the list, but it wasn't listed as one of them when you labeled it.
okay.
But it was just one, I think I saw that too.
I think it was at one time and I removed it because I just don't care for it. But I'll be glad to talk about it. We're dealing with 3 parachutists reach terminal velocity at the same distance above the ground below. So for fastest to slowest, rank their terminal velocities. Recognize that friction, air resistance, depends upon how fast you're going. There are a couple other factors also. Surface area is a big thing, but if all the parachutes are at the same surface area, it's really gonna come down to how fast they're going. And terminal velocity is the point in which they are in equilibrium. Their velocity, they've reached their final velocity, it stays constant. Close enough. So if they're in equilibrium, person in a parachute, there's the force of gravity acting downwards, And then there's this air resistance acting up, we'll just say force of air. So the person who weighs the most will have the greatest force of air. Well, weight is equal to mg. G is gonna be relatively constant for both of them. It even states that they hit their terminal velocity at the same distance from the ground. So the air resistance will be greatest for the one with the greatest weight. And since air resistance is dependent on how fast they're going, the one with the greatest weight will have the greatest terminal velocity. And the greatest, and in this case, the greatest mass will correspond with the greatest weight. So C, A, B would be the list from fastest to slowest. And then rank their times to reach the round. I don't know if the typo has been fixed in your books. Does it say ground or round?
Round. This is round.
Round, okay. I saw that and I was thinking, what is the round? But then I realized. So since they all were the same distance from the ground, the one that's traveling fastest will get there in the quickest time. So they wanted to rank it from longest to shortest, and so it would be the reverse order for time. Is that?
Yeah.
Good? Okay. Other questions from chapter 4? All right, any questions from chapters 4 or 5? So if something pops up again from 4, feel free to ask. Just, there's less flipping back and forth doing it this way. Any questions from chapter 4 or 5?
Chapter 5, deep and soft, number 28. I didn't really, I guess didn't understand, green square, 4 square, 5 square,
Right, you said number 28?
yeah.
So if you stand next to a wall,
Or, no, sorry, 29.
29, forces of 3 and 4.